So today we get to the long-awaited Ampere's law, but I would like us to build our way up to it again. It's actually important to my teaching here, but it's important for you to review. So will you please on your worksheet, before I drag this box away, put down an expression of Coulomb's law. Stop the show, do it. You started the show again, and hopefully you have something like this. You might have had F is equal to, and then a couple of Q's over R squared. This is, or alternatively, dE is equal to this quantity dQ over R squared. Then we have this awkward form here, which you may or may not recall was leading up to Biot-Savart. But first, let's stay with electrostatics and go on to Gauss's law. No, let's not. Let's do Biot-Savart next, where you're dealing with a magnetic field instead of electric field, and you did an exactly sort of a parallel to this, except that an element of charge that gave rise to magnetic field was a little bit of current, an IDS, and so that is going to replace the dQ, and then this epsilon naught, the permittivity constant, is going to be replaced by the permeability constant, and it's going to be on the other side of the fraction bar. Okay, so you have that, which all that talking through I did, I hope helps you with remembering and being able to construct these again, which you will be asked to do. Cross product there. Okay, and then the more elegant Gauss's law, and you have written that down at this point, and so we're starting the show again, and you have this, that the charge enclosed, the net charge enclosed gave rise to the field at the surface. And the idea was that we would go over the whole surface, hence that circle integral, Gaussian integral, and go over the whole surface looking at the dot product of the field at that little patch of surface and that little patch of surface, and add them all up. And if we had a net charge enclosed that was positive, then there would be these arrows would be going out. Here I can make this go out. These arrows would be going out everywhere as you went around, and so it would add up to a net positive flux, indicating that there was a positive charge enclosed. Oh yeah, we remember all of that. Well, and if there was no charge enclosed, then the you would have as much field going in as coming out. Maybe there was some external source of field here, but no source of field inside. Then there would be negative flux and positive flux, and it would add up to a net zero, indicating that there was no net charge enclosed. Oh yeah, we remember it all. Okay, now to Ampere's law, which instead of dealing with electric fields is going to deal with magnetic fields. That we're going to go from the E to the B, and the source of a magnetic field, the source of an electric field was a charge, but the source of a magnetic field is going to be a current. So it's going to be the enclosed current that we talk about here. The current contained. It's going to give rise to the magnetic field. notice that we've gone from permittivity to permeability. It's flipped over to the other side. We're still going to go all the way around, but this time it's not going to be all over a surface. This time it's going to be all the way around a circle. And we're going to take the dot product of B and ds as we go around that circle and see if it comes out to a net amount, that would mean that there was a current enclosed, or a net current enclosed. We don't know the details. And if it comes out to a 0, that means there's no net current enclosed. Let's consider applying that. Let's start with this external current. And if that current's coming towards us, and so we do the curly straight, and we get that you have this magnetic field. If you were to traverse this Amperian loop, this is called a Gaussian surface, this is called an Amperian loop. If you were to traverse this Amperian loop in the direction of this arrow, then as you came along here, the dot product of the magnetic field here in green and the path, ds, would produce negatives there. But when you come over here, the dot product of the traversal of the loop and the magnetic field is going to produce positives. And you'll have to trust me. Here the magnetic field would be stronger, but there's going to be a smaller amount of it. Here the magnetic field would be weaker, but there's going to be a larger amount of path that's going that way. And it adds up to 0 if you go all the way. Let me get this out of here. Come on. Now, if you take this current that is enclosed, then again, curly straight gives us that the magnetic field is going to encircle it like that. And over here, your traversal, and the direction of a traversal is very important. Your traversal is going to be contrary to the magnetic field, so it's going to be negative there. And when you come over here, it's going to be contrary to the magnetic field. So it's going to be negative over here. It's going to be negative everywhere. And when you add them all up, you'll get a net negative, indicating that there's a negative current enclosed. And we say that that current away from us is negative because if you take your right hand and do a curly straight and let your fingers go the direction you're curling, then your thumb is pointing up, and that is our convention, is a positive current, and this one, which goes contrary to the thumb, is a negative current. Finally, if we look at this one here, we look at this one here, the magnetic field encircling it as curly straight gives it to us, and here it's going to be with the traversal, and the magnetic field are going to produce a positive dot product, and here they're going to produce a positive dot product. You get a net positive when you add them all up, and that means that there's a positive current enclosed. Again, let me repeat. If we had chosen to traverse the loop in this direction, take your fingers and make them go around the loop that way, and you'll see your right hand thumb is going in, and that would make this be a positive, because it agrees with the thumb now. That would make that to be a positive current, and this would be a negative. And notice, when we're just dealing with this one, this negative current, here the traversal is contrary to the magnetic field, and here the traversal is contrary. That becomes out to be a negative current enclosed. Okay, now that should be kind of sweet, and it would be very lovely, except that Mr. Houghton gets all niggly about your applying Ampere's law, just like he did with your applying Gauss's law. And maybe this time you'll learn how to do it. So I start with a current, and I'm interested in the magnetic field. And the first thing I do is to draw an Amperian loop around that current. I'm interested in the magnetic field out here, but I draw a loop which passes through the place where I want to know the magnetic field. And just like with Gauss's law, symmetry is going to be very important. We could talk about the behavior for this Amperian loop, but if you tried to evaluate the integral for that, it would be craziness. So we choose a nice Amperian loop and we describe it. It's a circle. Its radius is r because I want to know the magnetic field at r away from the current. And the loop has its center at the current, at the wire. You need to tell me all of that stuff. And then you would assert, nope. You need to talk about how you're going to traverse the loop. And I choose to traverse it counterclockwise. You need to tell me that, or at least say as indicated in the diagram, but you need to explicitly say how you're going to traverse the loop, and then you talk about the magnetic field at that loop. That you would say that B is everywhere the same because we're all the same distance away. So B is constant, and B is everywhere parallel. Now, I could have chosen to traverse the other direction, and then that would make B anti-parallel, and I would need to say that. But notice that because I chose to traverse in this direction, that makes this be a positive current. If I had traversed it in the opposite direction, then that, when you do your curly straight, you find out that's a negative current. And indeed, if you're everywhere anti-parallel, you're going to add up a bunch of negatives, you're going to get a negative current. It all comes out in the wash. But you need to be explicit and intentional, not just lucky. Okay? Then I want you to talk about, to write Ampere's law. And then we would evaluate this integral. We would say, well, wait a minute, B is everywhere constant, so I can pull it outside the integral. It's not a function of where I am in my path. And B is everywhere parallel to ds, so I don't get a negative out of that. And so you end up with B integral ds, but you know what it is if you add up all the ds's everywhere around. That's just the circumference. I moved the permeability constant over to the other side. And then I solve for B. That's what this was all about, is what is the magnetic field at some distance r from this current. And you see again we get buoy over the sea, but much cleaner. Okay. Every single one of these steps and that picture I expect to see when you apply Ampere's law. Ah, well, let's do it. Here you have a cross-section of a wire which has a uniform current density of I divided by the area, and that current is coming up towards us out of the page. And I want to figure out what B is. That's what Ampere's law is all about. Finding out what the magnetic field is at a distance r. Well, we already know what the B looks like at a distance r outside of the wire. But what about inside? And I want you to do this. I'll talk it, but you could stop the show so that you do it as far as you can. That's when you become the master, when you can do it. Okay, so I'm talking. First, we need an Amperian loop. Well, I want it at this distance r. They've already drawn an Amperian loop, and they've already indicated a direction of traversal. Very good. Then I would talk about B, which I would like to claim is constant, and if the current is coming up out of the page, it's everywhere parallel to that traversal. Then I would write Ampere's law, and you try to do that from memory. Don't go back to the previous slide until you've tried it. Then you can go back and see if you did it right. And then, since b is constant, I can pull it outside the integral, and then you're just evaluating this value. But you need to be very careful that it is the current enclosed. How much current is enclosed here? It's not all of I. It's the fraction of I that corresponds to this area relative to the area of the whole loop. So you be sure to do that. Yeah, okay. I guess I wrote that for you on your worksheet, but you should be able to write it. Okay, and you come up with an expression for r inside of the loop. Hopefully you recall the expression for b outside the loop. If not, you could derive it, but this time you would have the advantage that all of I would be enclosed, not some fraction of I. And then what I would finally like you to do is to make a graph, as you will be asked to do many times, of the magnetic field as a function of r. Here would be the edge of the current carrying wire. So what does it look like inside? What does it look like outside? Remember, if there's a significant event that happens here, you ought to try your best to indicate at what value that happens. Good luck with that. And here is a checkpoint, lovely checkpoint that I have tried to improve your vision, that here the wires are going in front of these current, here the loops are going in front of the currents, and here where I haven't darkened it, the loops are going behind the currents. So you need to do that checkpoint. It's quite a lovely challenge for you. Now I want to talk about solenoids. Here's a solenoid, especially if you were sending current through it to get magnetic field. So here is this solenoid has been laid on its side. You're only getting the wires in the front. There is a golden other half of that current going around the back. Here it loops over to here, loops over to there, and so on. And when we send current through those wires, you can see that you get a magnetic field encircling the wires. And then as you go out, here the magnetic fields from the various these wires superimposes to make the magnetic field look like this. Instead of continuing to be circles and circles and circles, it comes to look like this, that you get this magnetic field through the center, which is fairly uniform, and this magnetic field around the outside. And I hope you would be able to see from the density of the lines that the magnetic field is much weaker out here. In fact, if we make this a long solenoid, we would claim that the magnetic field out here is 0. Really? 0? How could that be? Well, first off, I think on your worksheet I had asked you to say whether the current was going down or up, that you ought to look at these magnetic fields and tell me about the direction of the current there, and the direction of the current there, and hence the direction of the current in this wire here. But consider this center current right here, which does go out and out and out, but they start to superimpose. But way out here, the magnetic field from this current carrying wire is going to be weak, but there's going to be a lot of them from all of these superimposed. And here the magnetic field is going in the opposite direction. And the net effect is the magnetic field from all of these wires and the magnetic field from a fewer number here adds up to a zero. That if this is a very long solenoid, you get no magnetic field out here and uniform magnetic field in here. Still at the ends there would be fringing. Okay, we need to come up with a formula for the magnetic field from a solenoid carrying a current I. And we're going to start with the magnetic field from one of these currents. So I take a loop. Let me get rid of this. I take a loop here and no, God darn it, that's not what I want to do. I want to deal with this picture. All right, so I want to look at the magnetic field outside and inside of a long solenoid, and up here we sort of developed the fact that you get a uniform magnetic field inside and none outside. So here is my choice of Amperian loop, this reddish rust loop. And out here the magnetic field is zero. So when I'm going around my loop, I get no contribution there. B is zero there. Here, along this part, here it's going through a magnetic field of zero. Here it's going perpendicular to the traversal. The ds is perpendicular to the magnetic field. So when we dot product, we get a zero there. So we get zeros along that edge and that edge and that edge. The only place we get a non-zero value for evaluating this is across here, and there B and ds are going to be parallel to one another. So you can pull the B outside, it's constant, and then you evaluate the ds and you get an H. And so for this particular solenoid, the magnetic field outside is zero, and inside it's going to be equal to this, well, all of the current enclosed. That's awkward. How do we talk about that? And I'm going to introduce a new thing, which is the turn density, the wire density. How many wires per meter do you have? How many times is a current repeated every meter? And so the current enclosed in this thing would be equal to I times the turns per meter times how many meters long that was. So there you get the H. But it's the same H we have over here. And so we have a very nice result that for a long solenoid, which has a uniform field inside and no field outside, that magnetic field that you have inside is going to be given by the permeability constant times the current flowing in the solenoid times the number of wires per meter. And it reads, it's got vowels and consonants, and it reads boing, boing, boing. Exactly the sound you would expect a solenoid to make. What a wonderful mnemonic. And you're going to apply it a lot.